So what we have to cover in this unit, I mean, they'll call it the thermodynamics unit, but again, the term enthalpy might be something new to you. As hopefully you've seen a little bit today, and I was talking to another group about next class with calorimetry as kind of review of what we did in Chem 1. We try to keep terms away from Chem 1 when possible, because big words are confusing and intimidating to tiny little Chem 1 students. But you guys are big boys and girls, so we have to talk about things like what is thermodynamics and what is enthalpy. So again, first off, thermodynamics is just that conversion of heat to and from, and then other forms of energy involved as well. One of the things that we did talk about in Chem 1 was the first law of thermodynamics, which we just called the conservation of energy law. And energy can't be created or destroyed, just converted from one form to another. That's why when you did your reading guide, if the system gained energy, the surroundings lost energy, or vice versa. So you have to keep track of the total amount of energy involved in any process. Now, just like on your final exam when I had questions dealing with error analysis, boy, this is a good one too. Because think back to your styrofoam cup calorimetry. Is all the heat contained within there? No, it's lost to the air as well. There's a source of error, that being the air. Try to enunciate that so we know one from the other pretty well. So again, we have to go over a lot with this. A little bit is going to be review from what we did in Chem 1, but even today, the first calculation I give you is a new calculation. It's kind of stoichiometry based. So if we're good at stoich, today's math that I have to show you should be fairly straightforward. My next slide has one more term, and then I want to get into the math with you at that point. So again, didn't want to give you a lot of conceptual stuff today because I'm hoping that the reading guide, just reminding you of energy transfers, is good enough to kind of start off this unit. You're going to see plenty of that over the coming days. Okay, I'm going. So enthalpy. Now first off, enthalpy is given a symbol of delta H. So it's a capital H, you know, delta is the triangle. Enthalpy is trying to give the numerical value of the heat exchanged. Now lowercase q, as you will learn next class period, also stands for heat. However, that's just a total amount of heat. Enthalpy is typically going to be how much heat per mole. There's actually known values for enthalpies for reactions, known values of enthalpy dealing with particular what's called heat of formations, bond energy. So there's a lot of different ways we can find that enthalpy, and that we will be. So this is the only term I have on this slide, because the other thing that I'm going to show you right now is a short animation reminding you of that idea of heat flow of one thing to another. Oh. Who needs a video when we can start to do math instead? Now, I don't know if you want to write this down, because what I'm going to do is just switch over to the smart notebook and write it down and show you my work instead. So that might be better than writing the words to the problem. But a typical problem that you need to solve for today that I think is kind of stoichiometry-esque is we can give you the enthalpy, the delta H, for a reaction. Notice that's a negative, so this is an exothermic reaction. And we can give you an amount of one of the reactants, or quite frankly, products, and ask you how much heat would be created in this particular instance. Okay? So again, I'm going to switch over to Smart Notebook and write this all out for you in, equation form instead. So we'll come back to that if need be. So the reaction was white phosphorus burns in oxygen. Now, if you've ever heard of diatomics, well, phosphorus can actually exist as a P4. In fact, sulfur can be an S8. in AP chemistry, it's very common to be given the equation for things. I mean, you just took a reaction unit test a little while back. I didn't ask you to write reactions. In Chem 1 might have you do that, but not in AP because it's given to you. What you're going to see more in this unit, that not only is it common to be given the reaction, they give you information after the reaction. For this one, the enthalpy. Now, in this question, I started off with 266 grams of the P4. That's what was given to me. And the question asked, how much energy is produced if I combust 266 grams of P4? First thing you have to do when you're given grams of anything in this class all year long is convert to moles. When in doubt, figure out your moles. Now this is for P4. So I took the mass of P, times it by 4 to get 123.88 grams. And if it helps with you, if you're someone who likes to do one step at a time, that's 2.15 moles. But once you're in moles, now if that's how many moles I have, and on the far right hand side of the smartboard is how many kilojoules per mole, I'm basically using that as a conversion factor. The moles will cancel out. Now this is probably the simplest problem I can show you with this. I want to show you one more here in a minute. And then we're done with notes. But again, if that delta H is how many kilojoules per mole of that reaction, figure out how many moles of the P4 I have, multiply it out. Because again, remember, units are canceling out when you do conversions. Grams cancels out there, moles cancels out there. I get the kilojoules. I'm going to flip back to the PowerPoint just to show you the second question, but then I'm going to come back to here and write out the second question again. So again, you probably don't have to write down from the PowerPoint. But here's the second question we're going to do, and the last question we have. It says, how many grams of oxygen is needed to give off 1,600 kilojoules of heat in a combustion reaction with propane? And once again, I give you the delta H value for that. So why I picked this problem is you're kind of going in reverse. You're solving for the grams. The first question you solved for the amount of energy given off. I want you to be able to go in either direction. So, again, typically on a test you would be given the equation, so I'm just going to give you the equation. C3H8 is propane, plus 5 oxygens gives me 3 carbon dioxides, 4 waters. Any combustion reaction is going to be exothermic, 2044 kilojoules per mole. In this particular problem, the number that we were given to start off with was negative 1,600. It said 1,600 given off. That's why I put the negative sign in front of it. If I didn't, and you did the rest of your math, you'd end up with a negative grams. Hopefully you realize that, just make that a positive then. You don't have to necessarily call this per reaction, but it might help out here in a minute. Because the first thing I'm going to do then is I'm going to use a conversion to cancel out my kilojoules. And how I can do that is by using the enthalpy value given to me in the problem. Notice that all I did was flip it upside down. If I do this, that cancels out. For every 1 mole of reaction, it gives off 2,044 kilojoules. But if I only gave off 1,600 kilojoules, how many moles of reaction do I have? That's basically what I'm trying to figure out to begin with here. If you remember when we did reaction rate, and if I gave you the rate of a reaction, that rate of the reaction was also the rate for anything that had a 1 coefficient in front of it. The same stands true here, which is why in the previous problem, when I converted to moles, since there's a 1 in front of the P4, I was able to immediately convert to kilojoules. The reason why I bring this up is this question is asking about the oxygen. How much oxygen do you need? There is not a 1 coefficient in front of the oxygen. And that's where this is a little bit like stoichiometry. Because if right now I have 1 mole of reaction, I need to get to moles of oxygen. And there's 5 oxygens for every 1 reaction. This is the step that students typically don't do. They know how to convert from grams to moles. They know how to multiply by the enthalpy value. But if it's not a 1 coefficient in front of whatever you're solving for, that's where the mistake comes. But now I'd be in moles of oxygen. And if the question asks for grams of oxygen, I just have to multiply by 32 grams per mole. If I abide by sig digs, that would give me 130 grams of O2. That's how much is needed to create that amount. So our calculation today that you need to learn and that your web assignment is going to be based upon is using that enthalpy value and a conversion factor. Either I give you the starting amount of something like I did in the first problem, and you have to figure out how much energy is given off, or I give you the amount of energy, you have to figure out how much did I need to make that happen.